Hi, guys. Sorry, erasing stuff from yesterday. Class starts in a few minutes, but I was trying to get here and get ready and mostly make sure that we didn't have the same technical difficulties that we did yesterday. So we'll just kind of hang out for a few minutes. I'm going to keep getting stuff set up. So if you are here, because we're starting to write for class, go ahead and get out something to write with. If you have another device, we're going to start on page 1, slide 1 of chapter 7, which is periodic trends. So we're going to start with that here in a couple minutes. If you have any questions, I think the comment box is on this side. To be honest, I have no idea where it is. Somewhere there's a comment box. So if you have one, go ahead and ask. If you don't have any questions just yet, we'll all just hang around until, for, I don't know, like a minute and a half or so, just to give people a chance. Then we'll start with our usual announcements and the like. Where is that information? I posted, so on Canvas I'm trying to stick with the usual bins and buckets and everything else. Ooh, we have a question about SI. So I got an email back from Megan, and she said the SI email is buried in everything else. I would check your Osprey email account, and I would, yes, we can see Lily in just a second. The Osprey account, check that email and check the Canvas email. Megan, since you're here, where would they go to look for an email that says where the links are? Megan, in the comments box, which you may not be able to see on a cell phone, says that the sessions tonight at 5 and one tomorrow at 6. She's sending a Canvas message. All right, hold on. There's a lot of comments. This is my favorite part. Makes me feel real ADD, but I love it. Okay, so Chris asks, does the Quip go live after class? Yes. So at 4:15, and I turned off the internet on my other computer because there's not really enough internet in my house to do this. So it is on Canvas. There are 2 of them. So one is just a score placeholder, and the other one is the Quip. The one that opens at 11 or is due at 11:59, then that is the one that you need to look at. I will go in and make sure that that's clear. I will also send a Canvas announcement with a direct link into the Quip that is due today. It's due today. It's on Electron Configurations, which is what we talked about on Monday. So let's see. Trying to make sure I get all the questions. If your Canvas messages, so if you get the things that I sent, like my weekly updates, that is the same way that you will get Megan's email or Canvas message. I am copied on those. And so if I get that, I can send you the information directly as well. And I will do that to the student who asked specifically in case you're having some issues. Hey, you want to come say hi? Lily, come here. My students would like to meet you. Whoops, hey, Lil, pay attention. So that was probably the most embarrassing thing that could have happened to my dog, to have a meltdown about the idea that she was going to be on YouTube Live. So we'll try this one more time. What do you have to say to them? She thinks we're doing great. She also is super happy that we're all here. In the announcements on Canvas, so there's a folder that has regular ones. I included a super cute picture of her where she says it's her best day ever. So I will try to provide as many dog pictures as possible because everyone loves dogs. And if you don't, I don't own a cat. but I will try to get some cat pictures for variety. So stay tuned. Okay. Any other questions? Let's see. Hey, you're fine. I'm glad you guys like the dog. Me too. True Life, I locked her in here so that she would come to Gen Chem 1 because it's the best and everyone loves it. So I'm going to turn on a lamp because it feels dark and cave-like in here today. If you have any questions, you can put them in the chat. Oh, wait. Oh, no, y'all are fine. Keep asking questions. This is how this works. So for the quip, please write it in long form, which means you will need to use the buttons. So to get, not to get, we'll take pictures of animals. You can email me. So for the long form on Canvas, you can either write like 1S, 2, if you are pressed for time and using a bunch of formatting tools makes you feel like you're not going to be able to complete your quip on time, you can also do 1S. Let's call this the caret symbol. We all know what symbol that is. I have no idea, but it looks like an upper triangle. Let's use the upper triangle to indicate that it goes up. Both of this or this in formatting will be correct. You do need a period in the like text. I think I just said you need one. If you do not have one, I can find one for you. But either of these, so do not, definite hard no on the noble gas. Perfect. Okay, hold on, I gotta move this chair somewhere so that I have a little bit more space for our learning environment. Are you gonna sleep right there? Okay. So if you could, so behind this, I have another computer, because that's how we roll in the digital age, with the slides. So we're gonna start on, oh, it's really choppy. No noble gas, do the long way. I can see that it's trying to glitch in and out. I did also notice that YouTube will no longer be allowing you to have high definition videos. I'm not sure what that is doing to the stream. We'll go from there. Sorry about that. But we're going to start talking about chapter 7. So chapter 7 is, I don't want to call it an easy chapter, but unlike some of the other ones where it has lots of math and lots of other types of things, this chapter 7 is about periodic trends. So if you have a periodic table, great. If you don't, I will draw sketch out periodic trends and adjust them in that way. So in chapter 7, there are, on slide 2, it tells you that there are 8 different subsections, right? So section 0.1, 0.2, yada, yada, yada. So we're only going to talk about sections 7.1 to 7.5, which is an introduction to the periodic table, followed by 4 discrete periodic trends. The rest of that chapter, we are not going to talk about. You are more than welcome to read it. Don't forget, there is a link to a open access textbook if you want to use that. Open access just means free. So it is as close as we can get. I will post, so there are end of chapter problems for the textbook that we all own. I did look through the open access textbook, which has less end of chapter problems, but I've picked some, and there is a chapter 7 worksheet. And if we need more examples, I can try to write up a few more, just to give you guys as much practice as possible. So let's talk about the periodic table. So on slide 3, we know that the periodic table is essential for chemists. So there's a couple of different versions of this that we've seen. Yeah, that's not helpful. But I found a bigger periodic table. We still can't actually read this, But it turns out that people mail them to me all the time, and I didn't throw them away. So we have a periodic table. We'll stick it up here for now. But we know that the periodic table is essential, and we know that every chemist, or most of us, have one at our house. Sometimes it feels like I have like 10 different periodic tables, but we know that the periodic tables exist. And so when we think about the periodic table, there are a couple of, let's call them long-term things that are important. You're so cute. So we know inside any square, there's a couple of different pieces of information. If we think about potassium, it's element 19, and it weighs 39.10. So we have the symbol. We have the mass. And over here is the, good, we're still on the screen, atomic number. So the atomic number, like we talked about last time, is how many protons, neutrons, and electrons. Hold on. There are. Trying to get that glare off. It doesn't really work, but we'll give it a go. So the atomic number is the protons or electrons. What I would consider the important parts for any of these elements. The trick with all of this is that it's hidden in a periodic table. Today, when we think about a periodic table, we know that there are 118 elements and that they're organized in such a way. One thing that we learned in chapter 6 is that when we look at the periodic table, we can start to notice trends. So I don't remember if you guys did the flame test before we went on spring break in lab. And if you did, great. If you didn't, I think you get to watch a video. I don't really know what's happening. But we know that the periodic table looks something a little bit like this. And we know that these elements here all have one s electron at the end. So it's whatever the core is, and then just one more s electron. So the thing is, when we start to think about how all of these interact, it allows us to really think about, okay, well, if everything in this column is the same, what does that mean? So the periodic table is a guide map. Or you can think about it when we think, if you go to Instagram, which everyone is because we're all at home, so we just look at memes. Me too. But we know that if you go to sort, or you can look at a hashtag, and in theory, that should pull different things that are the same. Doesn't always work. Sometimes people don't use the right hashtag, or they use it incorrectly. So we know that anything in this column is going to be the same. So the periodic table was developed a long time ago. And so the periodic table was developed in the 1860s by two different scientists, Mendeleev and Mayer. And so the thing with the original periodic table is they didn't have 118 elements. They just had like about 60. And they were things that we knew: gold, silver, carbon, hydrogen. But the issue with the periodic table is that they started to leave holes where they knew they would be. So this is totally done because we're at my house today. But if we were in lecture, there are some of you that sit in groups. And so I would say like, oh, I wonder where so-and-so is. But a lot of times it was that they'd saved a seat because someone was running late, the line was on at Chick-fil-A, or whatever else. So we can save seats for people we know are coming. But they did this in the periodic table. So if you switch to slide 4, it shows this. It's in not English. It's a periodic table. And so they're in groups. So basically, if you look at it, this is the Mendeleev paper from 1871. So it's really old. Basically, we have buffering. I'm going to be honest. I don't know how to fix buffering today, but if you do, you can send me an email. I've turned off the internet on every device. Just skip ahead. I have no idea. We're going to keep going. Okay, good. Hopefully it doesn't buffer that terribly, but it probably will because that's how life goes. But we'll keep going. Ooh, Ginger says just refresh the live video and we'll keep going. Hopefully this will continue to work, but we're gonna keep giving it a go. So in the Mendeleev graphic that you can see in your slides, he sets aside space for elements that hadn't yet been discovered. Hold on. I have no idea how to turn down the quality, but I will figure that out for the next time. So, oh, we're on slide 4 still. Oh, not me. Good call. So in his graphic, he leaves space behind. So the space behind basically says like, okay, we think someone is gonna sit here. So if you scroll to slide 5, which is a table out of the textbook. So this slide basically are Mendeleev's predictions in the center column. So he was like, I think we're gonna have an element that weighs 72 grams per mole. And they discovered germanium, which is 72.59 grams per mole. I gotta be honest. Even now, I don't want to say super popular, but I'm surprised at how accurate his predictions are. My predictions are always terrible and most of the time wrong. So the thing is, the periodic table tells us a lot, both based on what the elements, what it says in the square, and where they are on the table. So periodic trends are going to give us 4 different ways that we can predict how elements will behave. You do not need to remember dates for that or the year. No, dates are years. Years or names of the people who discovered the periodic table. Don't worry about that. Just more like information. So our first periodic trend is the effective nuclear charge. So Z effective is the nuclear charge. So we can think about nuclear charge kind of like how well can you sense something from so far away. So nuclear charge is, we know that the nucleus has a positive charge. And we know that there are negative electrons out here. So the question is, how much do these two interact? So Z effective is the valence electrons out here, and we have a nucleus inside. So the thing is, sensing the nuclear charge doesn't make a lot of sense. But we know, let's give a real example. If we've gone to the mall, which is obviously closed, so we're gonna have to just remember how that works. Or on campus, when we walk past Chick-fil-A, it smells good, right? But I know, hopefully, you can't really smell Chick-fil-A at the student union because you're so far away. So, but as you get closer, you can smell it more. So the closer you are, the more you scent it. The more you scent it, the more you want to eat chicken nuggets. Might just be me, but we know I like Chick-fil-A. So the closer they are, the more you can feel it. That is going to be true for the positive charge and the negative electron. So the effective nuclear charge is how much these two interact, which is going to be distance related. So the bigger the nucleus, the further the charge goes out. The smaller the nucleus, the less effective the charge is going to be. So if we think about sodium, sodium has 11 electrons. So for sodium, and then we have the 1s, then we have the N equals 2 shell, and then we have 1 electron, and the N equals 3 shell. That's just saying that. So in this case, we have all of this interactions, and so we really can only ask about one at a time. And so when we think about a single charge at a time, we ask, how far is this? So you could use Coulomb's law. Coulomb's law, if you remember, which no one remembers. It's a lifetime ago. Coulomb's charge is the electrostatic potential of K Q1 Q2 over D. And we can still see that. So this is the electrostatic potential. K, yeah, we can still see. K is a constant. And Q1/Q2 is the charge. So this is the comparison between the nuclear charge, which in this case would be +11, and the charge on an electron, which is -1. So you could do that, and then the distance between those two. We will not be completing this calculation, just showing you where this came from. Again, we'll not be using this calculation. You could, but we're not going to. So the electrostatic potential is going to tell us that the further apart they are, or the greater the charge differential, the greater the electrostatic potential will be, which is great. But this is all about the Z effective, or the effective nuclear charge. So we really want to know how much this feels. Not like, does it feel hungry or does it feel cold, but how much of this charge does this interact with? So let's go back to our Chick-fil-A example. If you are in Chick-fil-A, the smell is really strong. If you're in a classroom down the hall, you really only smell Chick-fil-A when all of the doors are open, or if someone brings it and sits next to you, okay? But the question is about how many people have shown up or how much of the scent you can smell. So there's all of this region here. This part has what's called shielding. So basically, this is the number of feet or distance between the nucleus and the electron of interest. So the shielding coefficient tells you how much of this there is. So Z effective is the how much of the charge an electron senses. That's not how I spell that. So we can calculate this. Smart people, other people could calculate this. So Z effective is equal to Z minus S. So sometimes you may have also heard about Z effective as also being called Z star. It's the same thing, just two different names. So you don't need to worry about it. If you've learned it as Z star, the periodic trend will be exactly the same. If you only know Z effective, that's what the book calls it. Wikipedia sometimes uses Z star if you want to use that instead. So Z is the nuclear charge. So this is how many protons are there. So to determine Z, it's the atomic number. It's okay, we haven't talked about S yet. You didn't miss anything, Sarah. So S is the shielding coefficient. So if you remember back to the diagram of our positive nucleus and our electron out here, so there is what happens between our electron. All of these are the shielding. So shielding, it turns out, is there are a lot of ways you could calculate the shielding coefficient. In other days and times, we learn how to calculate S. Turns out it's not all that important. So S is a shielding coefficient. S increases the further out you get. So think about Chick-fil-A. The further away you are, the number of buildings that are between you, the less you can scent Chick-fil-A. The shielding coefficient basically just says the further away this is, the less of the nuclear charge you can scent. Okay, that makes sense. So if we think about, I'll give you guys a second to write this down. I am endeavoring to write slowly. You know what, we're just making it work. So if you slide to slide number 7, we're going to think about the plot for Z effective. So on slide 7, it shows you kind of a plot of what it looks like over time, and then we'll talk about what the trend is. So if we were to plot on the left Z effective and on the bottom atomic number. So atomic number basically is how many electrons there are or how many protons there are. So if you start, you can basically so down here at the bottom, the numbers, because they may not be easy to see, are 3, 10, 11, 18, and 19. Basically, as we plot this, it increases as you go across a row. Oops, a little deep. But what we can see is this jagged pattern. This pattern basically says across a row, Z effective increases, down a column, Z effective we get a slight increase. Oh, we've got a couple of questions about what S is. So S is the shielding coefficient. So it basically tells you how well or how much the nucleus is being sensed at the further you get. So S comes from a variety of different calculations that have to do with how many core electrons there are, how many core electrons, how many valence electrons, how many fully filled shells, how many partially filled shells. It basically is a measure of how far from the nucleus the electron is and how many things are in the way. So in that case, we will not be calculating S, and we will not be calculating Z effective at all. So we're just going to use the Z effective numbers, but this is where these numbers come from. So when we think about Z effective, if that's too high. If this is my periodic table, one of the ways that I like to think about this is a little different than the book. So a lot of people use the arrows to tell you where it gets bigger or smaller. That is a great plan. Personally, I find the arrows to be confusing. So when I draw an arrow, it is the direction in which we're going, and next to it is what the periodic trend is doing. So as we go across, we see an increase. As we go down, we see a slight increase. So all of this is to say that when we talk about atomic size, it will make a little bit more sense. But one thing we know is that as you go across a row, all of our electrons are being added into the same shell. So they can't really shield you because they're all at the same level. So in order for Z effective to really change, or to slightly change, you have to go to a new level. So this, as we go across, is because there's little change in shielding, but the nucleus is getting bigger. Z effective, for me, is what all of the other periodic trends are based on. So all of the other periodic trends are based on this one trend. So let's work an example. So on slide 9, which I'm also going to write up here, it asks us, what does it say exactly? Rank from high to low the following elements for Z effective: potassium, krypton, cobalt, rubidium, and selenium. So check my comments. I think we're doing okay. So in this case, there's a couple of things to think about. One, ranking should always tell you high to low, or it'll ask you which one has the highest, which one has the lowest. The other thing is, it's really hard to compare things that are not adjacent. So I promise, and that's Dr. Malcolm, not Alex, because we know Alex does whatever it wants. But what I can tell you is that all of these are they will be, can compare the sizes. Sorry, I think we have a lot of buffering on my end too. Still super sorry about that today. So hopefully we have an answer. So the lowest, or the smallest Z effective in this case, is potassium. So in my opinion, the easiest way to do ranking is to find the smallest and the largest, and then kind of fit stuff in the middle. So the largest is going to be krypton. So potassium and krypton are in the same row. So we know that in comparison, potassium is the furthest to the left and the highest up. So it's going to have the smallest Z effective. Anything else in this row, all the way across, which is about most of them, is going to increase going from left to right. But rubidium is the next one down. So we know that it's going to be bigger than potassium, but cobalt and selenium are way far away. So we know that this rubidium is going to be next. And we know that rubidium is just slightly bigger than potassium. And we're going to make the assumption that the increase from left to right is going to be bigger than potassium to rubidium. So how do we know which element is lowest on the periodic table? So in this case, for Z effective, because we know the trend increases from left to right, so in a row, it will be the lowest on the left. So hydrogen would have, well, hydrogen's a little weird, so we'll skip that one. But lithium has a really small Z effective. And then from here, we know that we encounter cobalt as we go across before we get to selenium. Whoops. Bad board work in my case. So this is an example for Z effective. Z effective will either be asked which of these is the biggest, which of these is the smallest, or something like that. So any questions about Z effective or Z star before we talk about atomic size and move to the next slide? Okay. So atomic size. Atomic size, basically on slide 10, we think about atoms and ions as these hard spheres. The highest Z effective is probably a noble gas, and it gets a little bit bigger as you go down the periodic table. So, oh wait. So potassium, no. So Aaron and Sam are asking what's considered the highest. I see your question. Let me rewrite that back up there. This is the lowest. This is the highest. You could have also written it the other direction, where you had krypton is greater than selenium, greater than cobalt, rubidium, potassium. I would have accepted either of these answers. I think in the slide it asked you to rank them from highest to lowest, and then I promptly ranked them from lowest to highest because I'm not really good at those kind of fraction things. So either of these would be accepted, both on a quip or an exam or the final in this case. Potassium is the smallest. Sorry about that. Any other questions? Okay, I think we're good. But we can go back in time. It's fine. We're just going to get where we get today and then go on from there. So atomic size. Atoms interact. So right now, we've mostly talked about atoms being by themselves, and we kind of think that maybe they could make a compound. We could try to make compounds of different sizes. And so, to be honest, in order for us to build elements or compounds, we have to get them to clip together. So thus far, we've really talked about our atoms as being just round spheres that basically have electrons at the end, and that's kind of the end of life. So in order to think about atomic size, we need to think about atomic radii. So if we if we move to slide 11, where there are two different radii types. So one radii is the, what did I call it on there? The non-bonding. So a non-bonding radius is the distance between the nuclei and the edge of the electrons. So a non-bonding radius is basically how big the sphere is, or the half of that sphere. So when we think about the non-bonding, it basically says this is about as far as it could go, right? So if by chance there was someone over here and we were holding hands together, nobody, well, I'm going to say nobody, and then somebody's going to send me an email and be like, that's how I roll my life. Most of us don't hold hands like this, right? I don't. I hold hands like this. So the distance between wingtip to wingtip is actually going to be smaller than if we're interacting together. So in that case, the non-bonding is basically how far it is from my nose to the tip of my fingers. But if I was holding hands with someone, the distance between my nose and their nose would be less than the nose to fingertip distance. So the bonding radius is half of the bond between two like atoms. Yikes. So basically, again, if I'm fingertip to fingertip with an identical Dr. Malcolm, which doesn't happen because I don't have a twin, but that distance between here to here is the non-bonding. As soon as the twin and I start to hold hands, it basically shrinks in a little bit. So we're really only going to talk about the bonding radius, not necessarily the non-bonding radius. The trends are going to be exactly the same, but if you want to calculate the bond radius, which obviously we're going to, you would need the bonding radius, not the non-bonding radius. So if on slide 12, we complete the following example, which I will read, hopefully slow, then I'll kind of write up how you solve it. So the question states, two hypothetical elements, X and Y, form XY2 with the structure Y bonded to X, bonded to Y. The XX bond is 2.04 angstroms, and the YY bond is 1.68 angstroms. What is the bond between X and Y in XY2? Now, also on the exam, I'm not going to read questions to you and just let you answer them. That's kind of silly. But the question is asking, if we have, what do we have? YXY, what is this bond distance? That's not very big. So I want to know how far apart these two are. But the data that we do have, if we X or Y, we know that in both of these compounds, we know what their size is. So the XX bond is 2.04 angstroms, and the YY bond is 1.68 angstroms. Now, angstroms is this A with a hat on it. You may remember that we've talked about angstroms as yet another weird scientific unit. An angstrom, so 1 angstrom equals 1 times 10 to the negative 10 meters. So it's basically something between a nanometer and a picometer. So in this case, it is just a smaller unit. You don't need to memorize this. It would be on your exam equation sheet, however that will work, which we don't know yet. We're not going to worry about it. But this information is not essential. Those numbers did come directly out of the problem, so they would come in a problem. On the exam or a quip or anywhere else, it would give you this information. These two came out of the problem, which is on slide 12 in the handout for chapter 7. So in this case, both of these bond distances would be provided. And so in this case, we're looking for what this distance is. So we know that in this case, part of this comes from X and part of this comes from Y. You can't see that at all. Now you can. So the thing is, when we think about where these two things come from, we know that part of it comes from X and part of it comes from Y. So one thing is it's half of the distance of X and half of the distance of Y. So if myself, we want to know how long this distance is, we can measure that by, I can't really get it on the screen, but you could basically measure my wingspan and divide it in half. And then if I was holding hands with someone else, you could do the same thing to them. So to determine the XY bond length, it's going to be half of the XX plus half of YY. And we can mildly see that. So we know that it's 1/2 of the XX, which is 2.04 angstroms, plus half of the YY, which is 1.68 angstroms. So when you plug this into your calculator, we'll get 1.86 angstroms is the distance between X and Y. It is 1.86. Good job. So again, this is how you can use atomic radius. So likely, this is a pretty simple question. You would be provided both of these informations. Both of this would come out of the problem. I think on Alex, It may make you go look at that, like here, go look at the table page, but I don't actually remember. But you would always be provided this. You don't have to memorize these in any way. So atomic radii, it turns out, have trends, kind of the way everything else does. So the atomic radii trend is relatively simple. So if we think about our periodic table, which looks something like this, the periodic trend is that as we go across, it decreases. Well, good morning. So, yeah, you don't have to yell. But 1.86 is the final answer. Should I say it in caps? Yes, it is the final answer. So the atomic trend, or atomic size, it decreases as you go across, and it's going to increase as you go down. As a right arrow, tell you the direction, which we can't even see. So it decreases in that direction, and it increases in this direction. So, which is different. The book gives you like arrows, whatever. Don't look at the book arrows. So atomic size decreases because Z effective increases. Ow. Left to right decreases because Z effective increases. And then we'll go down the table. We're going to increase because N increases. So I'll get a little closer for you. So as we go left to right across the periodic table, Z effective is going to increase. Z effective is the nuclear charge. So the nuclear charge is going to, or the effectiveness of that, because they can't get bigger because they're all adding into the same row, I guess, the radius is basically going to get smaller because the nucleus gets bigger. When it goes down a table, every time we go into new n equals 1, n equals 2, n equals 3, it basically moves that much further out. So atomic size is this way. Z effective is, so one question is Z effective the same thing as electronegativity? No. We will encounter electronegativity in chapter 8. Electronegativity uses part of Z effective, but Z effective is its own trend. Good question. Any other questions? Well, I was sitting on my notes. Can we think of Z effective as the opposite of atomic size? It's not necessarily Z effective and atomic size aren't the difference, because we get a slight increase when we go down the table for Z effective, where with atomic size we get a pretty much a great increase. So they both increase as you go down. So I would memorize them all in distinct manners in that case. So if you look at slide 14, it gives you different radii, so you can kind of see what they look like as you go across. Again, you would not need to do that. But what I meant is don't memorize it. So let's do an example. So arrange boron, carbon, aluminum, and silicon from smallest to biggest. So for periodic trends, it's always best to just think about who's going to be the biggest, who's going to be the smallest. So we know that boron and carbon are next to each other, and silicon and aluminum are next to each other. So we're basically looking at 4 elements that you cannot see. They're roughly right here on the periodic table. So we can basically think about them as one row over the other row. So we know that as we go down, they get bigger. So aluminum and silicon are going to be bigger than boron and carbon. But we know that it decreases as it goes across. So we know that aluminum will be bigger than silicon because it is more to the left. So aluminum is bigger than silicon. So we know that because these are, they're really going to be the boron and carbon, which are in a different row, right? So these are further down the periodic table. So then we can compare boron and carbon. So boron is further to the left in this case, and so it is going to be bigger than carbon. So this would be how you would rank those, or you could select which one is the largest, which one is the smallest. I don't want to say et cetera, but along those lines. So the other thing that is important is to think about what happens when these become ions. So if you gain or lose an electron. So what about an ion? So if we if we move to slide 16, I'm trying to pare down the slides so you guys, if you want to print them out, you can just look at them on your computer or your phone or your tablet or really whatever you work with. So the atomic radii, if you have an anion, so these are negative. These are going to be larger than the parent ion. So if we have oxygen, it will be smaller than oxygen, we'll just say oxygen 1 minus, which would be even smaller than O 2 minus. So when you add more electrons, the effective is going to go down because now you have more electrons with the same number of protons. So anions get bigger, cations these are going to get smaller than the parent. And so we know that if we think about certain cations, we know in this case that sodium plus will be smaller than sodium, and sodium 2 plus will be even smaller because you've removed electrons. So every time you yank off an electron, it's basically going to get smaller due to the nuclear charge being the same. So in both of these, all of the nuclei have the same charge, sodium versus oxygen. And so when you add the negative charges or the electrons, they're going to get bigger. When you take away electrons, they're going to get smaller. So isoelectric series. An isoelectric series. Ow. These are elements, elements or ions with the same number of electrons. So if you know what the noble gas configuration is, we're basically going to compare all of the different types of ions or elements that have the same number of electrons. It's not about the neutrons or the protons, it's only about electrons. So in this case, one of the things is as we increase nuclear charge, we are going to decrease the atomic radii. For example, O2 minus is greater than F minus. So if you put them in order of the nuclear charge, the atomic radii for the cations will be smaller than the anions. I don't remember if there is a ALEC objective on this particular thing. If there is, I'm going to take it away. So the isoelectric series is comparing electron elements or ions where they all have the same number of charges. And so as you increase the nuclear charge, the atomic radii will decrease. It's the only trend there. So there are two examples on slide 18 that you guys can work on if you want to. We are going to talk about the electron configuration of ions because it will help you for today's quip. So electron configuration of ions. This is basically asking where are the electrons if we start to lose electrons. So the electron configuration of an ion, we can start with lithium. We know that lithium has 1s2, 2s1. So it has 2s electrons, 1s electrons, 1s, 2s electrons. But if we create lithium plus, where did which of these three electrons leaves? It turns out that the electron in the outermost shell leaves first. So lithium plus is going to be Li, 1. It's going to be 1s2. So I can't remember what Alex prefers, but for me, you don't need to show that it's a 2s0. If it doesn't have electrons, you don't need to put them in there. So for lithium, this is our electron configuration. For lithium plus, we just remove the outermost electron. So if we think about iron, which is argon, 4s2, 3d6. No one can read that. So there are 6 d electrons in iron and 2 4s electrons. So when we create Fe2+, the question becomes, do we lose the d electrons or the s electrons first? It turns out that if we remember the orbital filling, we know that we fill the 4s first, but it turns out that once you fill the d electrons, or you put some in there, once you have d electrons, the s orbitals are easier to remove. So to create the transition metal ions, we remove the s electrons first. So we have argon, 3d6. So we remove s electrons So we remove the s orbital electrons first when we create a transition metal ion. That is only true for the transition metals. For the anything s and p block, you remove just the outermost electron first. So if we look at one more, let's look at two other examples. And these are coming off of slide 20. So let's look at Cobalt 3+, and we'll do sulfur 2-. So we can do this for both. I'm all over it. We're going to do an anion here too, because we can add them in. So for cobalt, we'll look at that one first. So if we look at our periodic table, which I know this is kind of mediocre, but cobalt is right here. And so we can count over how many there are. So we have 4s2, then 1, 2, 3, 4, 5, 6, 7. Hold on. So what I do is I just count the number of squares over, because that tells you how many electrons there are in any given orbital. So for cobalt original, so cobalt alone is going to be argon 4s2 3d7. So to create the 3+ ion, we need to remove 3 electrons. We're going to remove the s electrons and then a d orbital electron. So it would be argon 3d6. So all of the s electrons go away and one of the d orbital electrons, because we know that to be 3+, we want to remove 1 electron. So when we think about sulfur 2-, which means we're going to add 2 electrons, we need to first figure out what is the original. So when we look at our periodic table, we know that it's going to be neon 3s2 3p1 2 3 4. So when we add 2 electrons, those 2 electrons will go into the outermost orbital. So you can add them directly into the p orbitals to create s2-. So that would be neon 3s2 3p6. Now you might be wondering, that looks a lot like argon. So you would want to know, could you just write this? And the answer is no. So because you haven't gone to the next level, you can't just write argon as this. So there is a difference between a fully filled outer shell and moving all the way into the argon. So for this case, if you had sodium plus, you could write that it was just argon. But for something like this, where we added electrons, you need to indicate that it is still the 3p shell. So, any other questions? I've learned my lesson about erasing the board before people ask questions. That's correct, Kaylee. So when we make a transition metal, we remove the s electrons first, whether it's in the first, second, or third row. We will not make anions or cations out of the F elements. Mostly we're going to pretend they don't exist, so don't worry about those. But for the others, whatever the last orbital is where you add or subtract. Good question. That is correct. So to create a positive element, you've removed electrons, so you subtract 2. For a negative element, you added electrons to make that ion a negative ion. And that applies to all elements, no matter where we find them in the periodic table to make elements. So Sarah asked, can you add to the s orbital? You can, but it doesn't happen. So it turns out that the elements that create cations, typically you could give them an electron, but they will take, you basically give the electron and take it right back. We'll see that for so ionization energy is next. The one after that is, hold on, Electron Affinity, which is 4.5. And it's never going to happen for us to talk about it today. We'll talk about it first thing on what day is this? Today is Wednesday. The next time I see you on Monday of next week, we will talk about Electron Affinity. So for the next 10 minutes or so, we're going to talk about ionization energy. So ionization energy, if you were on your slides, we're looking at slide 21 real fast. So ionization energy is the energy required to remove one electron. So the thing is, if we want to remove an electron, how much energy does it take to remove it? So it's going to matter where it is in the orbitals, right? So ionization energy, or we often see this as I1, is the energy required to remove one electron. So you can only remove one at a time. But you can remove a whole bunch. You just have to pick, I don't want to say pluck one off at a time, but you just remove one at a time. So in this case, we can only remove one at a time, and that's, I don't want to say the best way it is, but that is how ionization energy works. So typically, we'll say for an element, any element, I1 is less than I2, is less than I3, which is less than I4. So this basically says that to remove the first electron of any element, it is easier than the next one. So that kind of makes sense because we're going to start to play with the shielding coefficient, which you still don't need to calculate. But basically, once you start removing electrons, the positive charge will overwhelm the remaining electrons and then kind of drag them a little bit closer. So as the electron removes the effective, it requires more energy. So if you look at slide 22, which is table 7.2, if you are following along in the online textbook, there's a table there too. But what that graphic shows you, and I will write up this series for at least one of them. So for aluminum, I1 is equal to 578 kilojoules per mole. I2 is 1,817. I3 is 2745 kilojoules. And I4 is 11,577. So we can see that I1 is 578. I4 is 11,577. So it takes a lot of energy to remove the fourth one, and even more than the third, the second, or the first. So the thing is, when we think about aluminum, there's a reason why this is so much bigger than any of the others. So for aluminum, we know that it's 1s2, 2s2, 2p6, 3s2, 3p1. So every time we go from aluminum to aluminum plus, 2 plus, 3 plus, then to create aluminum 4 plus, these numbers came out of the table that's on slide 22. You don't need to memorize these numbers. So the gap here between I3 and I2, this removes a core electron. So if you removed one electron, you would have, for this one, you would have a 3s2. Then you could remove 2 more and you would be back at 1s2, 2s2, 2p6. But to remove this from a fully formed core electron, it's going to cost a lot of energy. So when you do that, you can see these breaks in the ionization trend for a single element. So typically, the trend for ionization energy. We look at our periodic table. Whoa. So ionization energy. It generally increases as you go across. And it generally decreases as you go down. And so, to be honest, the ionization trend, if you were to look at slide 24, it shows you the ionization energies. It tells you that the highest ionization energies are for the noble gases. The lowest ones are for anything on the left side. And it gets, this is our lowest. This will be our highest. So when we think about this trend, we can actually put into account what is the highest or the lowest ionization energy. We can start to look at that. The other things that I like to ask, hint, hint, this is how I would ask it on an exam. And I have no idea if this is how it would be done, but it can be. So I1 for any element. So we're going to talk about, we'll talk about sodium. So I1 is sodium, goes to sodium plus 1 E minus. I2 would be sodium plus goes to Na2 plus 1 E minus. We could write I7 where Na6 plus goes to Na7 plus 1 E minus. So the way you can kind of think about this is that whatever the 7th, 5th, whatever ionization that is, it is to remove that electron. So we know that the charge on the element on the right side of the equation should be whatever that is, 7 plus, 8 plus, 92 plus 1 electron. And so this is just 1 minus that, because it's really important to remember that you can only lose 1 electron at a time. So There is an example on slide 25 that asks you to arrange them in order of increasing I1. So you can work on that. I will write the answer up once I erase this so that you can work on it at your own leisure. As a reminder, if you want to come to office hours tonight, you can just come to Zoom. So she either has already sent you a Canvas announcement or will do so shortly, where you can go into that and get more help working problems. Your QUIP is going to be opening in the next, 3 minutes. It's entirely possible that it is not open because I've somehow hidden it from you. I will fix that and double check that as soon as I stop streaming and get everything set up. So if you have any questions, I will answer those. So the plus, yes. So this here is just saying that you lost an electron from this component here. So it's plus 1 E minus. The 1 is not, I don't want to say not 100 important. So yes, you are correct. The QUIP that is due at 11:59 is the one you need to do. The other one is a score placeholder because fixing everything on Canvas. So the answer to slide 25 is over here. Yahtzee. For that one, it asks you to rank neon, sodium, potassium, argon, and phosphorus. The answer to that one is potassium, sodium, phosphorus, argon, neon. And so the way you would have determined that is that these are full shells. And the difference here has to do with the different rows. Okay, that is correct. It is on electron configuration of elements, not ions. You may see some changes to your ALEX objectives, but they are due on, for this lecture, they're due on Monday. The ones due tomorrow were from yesterday, Monday. All right, I will hang around here if anyone else has any questions. Otherwise, feel free to stop by office hours. I miss you greatly. And because I know we've all hung around to see her. Hopefully I don't fall apart here trying to show. There's my little nugget. I miss you guys. I hope you guys have a fantastic rest of the day. And Kaylee, I think you could have, depending on either of those, as long as you are, I like to call them the alligator clamps, go in the right direction, that would be fine. So I think that's probably right, provided that you realized that neon is the largest and potassium is the smallest. Miss you guys so much. Have a fantastic rest of your day. Stay safe. Oh, I'm back. To answer your question, Sarah, no, those are not. Sarah, Kristen, the cation anion examples will not be on the QUIP today. The QUIP is only on using electron configurations, not noble gas on whole elements.